It seems to make sense, right? So we'll talk about that again. We'll come back and talk about that. I just want to do one more thing, just double check 6571 is a prime number, actually. What are the chances that I pick a prime number? In one of my other classes, I picked a 8-digit number just out of the air, and it turned out to be a prime number too. So I have a knack of picking just prime numbers just by randomly guessing. The chances of getting a prime number gets lower and lower and lower as the number increases. In fact, for large numbers, large prime numbers, one of the biggest problems with computer security, or at least with cracking encryption, is how quickly can you find prime numbers. Okay, because most encryption technologies that we use today have to do with prime numbers. If you can come up with prime numbers really, really fast, you can crack encryption algorithms more effectively. So the problem is not to find factors of a number. It's actually to find the next available prime number. That turns out to be a problem to solve. Okay, so 6571 turns out to be a prime number. Using this method, how far do I have to go? I have to go all the way until I get 6571 divided by 6571 is 1 with a remainder of 0. Then I can stop. Okay? That means, I'm not going to finish this trace in this case. Okay? So, can I write an algorithm to do it? Do we have enough steps already to systematically determine how to do something like this?
Yes. Yeah.
Okay, very good. Do we have a loop? Are we doing something repetitively?
Yep.
Yes.
We are? Okay, so let's say loop and loop. Do we want this loop to be an infinite loop, or do we want to exit at some point? We want to exit when?
It's 1.
It's one.
Is 1.
When, sorry?
When the number is 1.
No, that's not how we do it.
When the number to factor is 1.
When it is a factor. Okay, so let's just say that when we find a factor. Okay, so we'll start with that and then we'll go from there. When we find a prime factor of the given number. Okay, wow, that's a long way of saying something that it can be captured a little bit easier in the next revision. So in the next revision, we identify that we have two numbers that we're dealing with. We're dealing with some kind of a prime factor. We're also dealing with a number that is given to us. So it is usually better to refer to these with their variable names. So in the next step, I just change and use the variable names. I would just say let n be the given number. Let f be the potential prime factor of the given number. So given these two variables, how do I re-express that condition? Do you guys have a question? No? Okay. So given these two variable names, how do we re-express finding a prime factor of a given number? What is the property of a factor? What are we doing with these divisions here? What are we looking at? Are we paying attention to the quotient, or are we paying attention to the remainder? We want a remainder of 0. Very good. So in the next step, we just say when the remainder of n divided by f is in fact 0. Okay? You can see that this algorithm is not really close to being done because I'm using words instead of operators. But that's because it is easier for me to think in terms of words first. If I can write down the words, like when the remainder of n divided by f is 0, I can write that down first, and then I can look up operators of a particular programming language and say, but how do I get the remainder of a division? If I don't write it down like that and try to think, all in my head, then I can lose track of my, thoughts, when I'm looking for the operator. Then I cannot remember, okay, but what was I trying to do before that step? So it's always good to kind of spell out everything and then you look at the previous step and say, okay, we are already at this point. How do I spell out the remainder of n divided by f, so that I can make sure that it is 0? As it turns out, there's a mod operator with most programming languages. So you can say when n mod f equals to 0, it is actually saying the remainder of n divided by f is 0. The mod operator is kind of like a division operator, except it does not give you the quotient. It gives you the remainder of the division. Are we okay so far with the mod operator? In C and C++, the mod operator is the percent symbol. In other programming languages, it is just spelled out as mod. Are we okay so far? Okay. So what do we do next? We have an empty loop body at this point, which means if nothing is being done to n or f, then the loop is going to become infinite because the condition will stay true all the time, or stay false all the time in this case because we have an exit condition. So what do we do in the loop in order to make n mod f equal to 0 happen eventually?
Divide n by f plus
No.
1.
What are we doing in the example? You got to go back to the manual example. Something got changed, okay? Something got changed from this to this, from this to this. What got changed?
Divide
The potential factor, right?
That's what I said. Divide n by f plus 1. Yeah.
But you're not stating what is happening to f.
F becomes F plus 1.
F gets f plus 1. Okay? I think you got the idea. We are adding 1 to something, but how do you express that in the algorithm? The answer is we are incrementing f for each iteration. F gets f plus 1. So that way, when we began with an f of 2, it became 3, 3 became 4, 4 became 5, 6, and so on and so forth. Very good. We are almost done, except we don't know what is the initial value of f, do we? And we have not identified whether this loop should be a pre-checking loop or a post-checking loop. So to finish this up, there are 2 ways to finish it. Okay, so I'll talk about the 2 ways. 5a is to use a pre-checking loop. If you want to use a pre-checking loop, then you have to say while n mod f blah 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 0 do and while. What do you think should be that blah 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 here? Remember, while is basically saying as long as. So in this case, go ahead. That's not equal to. Very good. Because we have to invert the logic. If the exit condition is when n mod f equals to 0, that means the condition to stay in the loop is the opposite, which means when it is different from 0. Okay, very good. So in this case, what should we do to initialize f? F should be initialized before the loop with a value of what? 2. Very good, because 2 is the first value or the first potential factor that we use. Very good. So that's 5a. Revisions 5b, which is an alternative. In this case, we use a repeat until loop, a post-checking loop. So with a post-checking loop, we still have to increment f, and then we use the exit condition as n mod f does equal to 0. But in this case, what do we use to initialize f? In other words, we still want to use 2 as the first potential factor by the time we get to the mod here. But because this is a post-checking loop, it always adds 1 first. So that means that f has to be initialized to 1 and not 2. Okay, so now we have 2 alternatives. Sometimes when you have 2 alternatives, they are 50-50. There's no preference to one or the other. In this case, there's a clear preference to one over the other. The pre-checking loop. Why do we prefer the pre-checking loop?
The number is first.
It is more clear, isn't it? Okay. The pre-checking loop is a lot more clear as to what is the first potential factor that we apply or we check. The second or the post-checking loop is not as clear because f gets initialized to 1, but we are not using 1 in the mod operation because it is a post-checking loop. By the time you get to the mod operation, f is already 2. So effectively, they are both the same. They do exactly the same thing. They have the same logic. But the first version or the first revision, the first alternative is more clear because it spells out what f is going to be by the time we perform the mod operation, whereas in the second version, we have to track down 2 statements in order to figure out what is the value of f by the time we get to the mod operation the first time. Yep.
I have a question. What is mod?
What is?
MOD. Mod. What is that?
We just talked about it.
Yeah, but like just the remainder.
It is the remainder of a division.
Okay. And then one more thing. When is f going to be like 0? When is that going to happen? Because like we say that f is not equal to 0. So
we didn't say f does not equal to 0. We say the result of the mod operation does not equal to 0.
Okay.
So in this case, when you look at n mod f does not equal to 0, or when it does equal to 0, it is basically saying that the result of the mod operation equals to 0. Okay. Any other questions about these two alternatives? Is it clear why 5A is preferred? Okay. In terms of efficiency, which one is faster? 5B is actually a little bit faster, but you won't know why until you get to the assembly programming class. The assembly programming class will explain because in terms of the assembly language implementation, 5A will require more branch statement or branch instructions, and 5B only requires one conditional branch instruction. That makes it faster. But in this class, we don't go for optimizations like that. Yep.
And 5A would be easier to modify to make it more optimized later on.
They're about the same. They're about the same in terms of optimization because it's just a matter of where the condition is located. So are we doing okay so far about this algorithm to find only one factor given a number? Okay. No questions about this? But remember that 6571 is a prime number. Using this method, how many iterations do I have to go through? 6570 because we start with 2. Okay, but nonetheless, it is 6,000 something iterations, which is a lot. Okay, so I claim that I can shrink the number of iterations to approximately the square root of this number 6571. Okay, what is the square root of a number like this?
81,
about 80? 81 or so. So that's a significant saving, right? Okay, let me just repeat what I said. I'm claiming that with the current algorithm, which is fairly obvious, that we have to perform 6,000 something iterations, right? Because we have to keep bumping up f until n mod f equals to 0. And since the number itself is a prime number, I won't find a number that is a factor of that until I get to the number itself, which is 6571. Since we start with 2, and each iteration is only adding 1 to the number, that means we have to add 1 about 6,000 something times to get to the number itself. Is that okay so far? So what I'm claiming now is I have a special method so that I can test only up to 81. Okay, I think it's maybe 81 or 82. Then I can conclude right away that the number itself is prime. I don't even need to go any further than that. Would that be a worthwhile saving? Okay, cutting down the number of iterations to approximately the square root of a